going to talk about building stream processing applications with Kafka, and especially focusing on the newly introduced exactly once guarantees Kafka provides. Before we get started, a quick overview. So Kafka is a distributed stream processing platform. People who are familiar with Kafka for many years might have a different perception, because Kafka originally started out as a message broker system. But it evolved over time, and now it's really a complete platform where you have a Kafka cluster in the center. You have producers that input data to Kafka, or consumers that read data from Kafka. Then there is a special connect framework where you connect to other systems, also to import and export data. And then there's stream processing capabilities, what we call the Streams API. And this whole ecosystem makes it a very powerful platform for your stream processing. Also, talking a little bit about Confluent. So Confluent is founded by the original creators from Apache Kafka in just 3 years. Headquarters is based here in Palo Alto. And what Confluent does is, first of all, we are all Apache Kafka, so we are the main contributor to Apache Kafka. And we also build our own platforms that we call Confluent Platform. And Confluent Platform consists of two parts. We have Confluent Open Source, that is Apache 2 license, and then we have Confluent Enterprise. And we basically make Kafka enterprise ready with this platform. So for Confluent Open Source, for example, we add more clients in different languages, because the clients that come with Apache Kafka is just Java. We add a schema registry, we add a REST proxy, and many more things. On the enterprise level, we have monitoring tools like our Confluent Control Center that helps you to monitor your applications and the health of your cluster. And recently, we also started Confluent Cloud. It's still not GA, but we have an early onboard program that runs already for a couple of months. That's basically Apache Kafka as a service, fully managed from us for you. Our latest addition to Confluent Open Source I want to mention is KSQL. That's a streaming SQL layer on top of Apache Kafka. It's basically a developer preview, so it's not like production ready. But if you're interested in this, check it out. It's on the GitHub repository, and we're happy to get feedback for that, because of course we want to build this SQL experience as good as possible, and we of course rely on users trying it out. So now coming to the topic, how you actually build applications with Apache Kafka. And with this, you have two main APIs you can use for that. So one API I mentioned already is the Streams API. It's also called Kafka Streams. You might have heard of that, if you know. It's a client library. Actually, it's much more, but you use it as once because you include the library into your application code like any other library. There's no difference in that. And then Kafka Streams help you to build your application. I will go into some more details. I cannot give a complete introduction to the library itself. It would be a completely own talk. I just highlight the important things that are important to talk also about exactly once semantics. And the other way is you can go with lower level APIs, like do-it-yourself, using the plain consumer and producer API that is actually leveraged under the hood in the Streams API. It's also a library you include, and then you connect to your cluster. So what it means is, when you build a Kafka Streams application, on the one hand you have a Kafka cluster that holds all your data, and on the other hand you deploy your app, but you don't deploy it on the cluster, you deploy it as a regular Java application. There's no difference whatsoever. You don't have a dedicated compute cluster, you just deploy your app. And within the app, you use the Streams API, and the Streams API takes care to connect to the cluster, read data to the cluster, does processing, and writes the result back to Kafka. Because it's a library, and you don't have a dedicated compute cluster, you can deploy your application in whatever way you wish. You have full flexibility from like a little bit old-fashioned WAR file all the way to the newest like Mesos or Kubernetes. It's a library, it's completely agnostic. You just deploy a Java application, but still you get stream processing capabilities that are very powerful. What other stream capabilities you get? First of all, if you use Streams API, it's the easiest way to go with exactly once, so it's just like a high-level thing. So what you get here, we have a very powerful DSL, where we have operators like filter, aggregation, windows, joins. We have a support for tables, and also for more low-level APIs like punctuations and things like that. We support very rich time semantics, so event time, ingestion time, processing time. And even if Kafka Streams is just a library, it makes the application elastic, scalable, and fully fault tolerant, including state. And that makes it applicable to all kinds of use cases, from very small to very large. So that's a big difference to basically Spark or Flink or whatever. Even if you have a library and you deploy a regular application, you get basically all the same guarantees those systems can give you, but you don't need a compute cluster that you need to manage, and that is of course very cumbersome. So to highlight here, if you want to enable exactly once with Kafka Streams, it's just a configuration that you give to your program, and Kafka Streams takes care of the rest for you. So why is it important? So what does Kafka exactly once guarantee actually give you? So on the one hand, it avoids duplicate writes into your Kafka cluster. And that means it frees your application from including deduplication code. So if you write an application and you don't have exactly once, it might happen that duplicates are in your data when you write. And then your application needs to take care of those duplicates. It needs to handle it. And that's like super, super hard. But with exactly once, this requirement goes away. And that means it simplifies your whole application development because it simplifies your code base. With this, we enable new use cases that require strong consistency guarantees. For example, in the stock market, in the financial industry, if you say, I need to build something, somebody, and you would say, hey, I bill you twice because I have a duplicate write, that would be very bad. That's something you can't do. For this, we need those strong guarantees in order to build a correct application. So now I want to go into some core concepts of the Streams API. So what you can do with it, how you can handle your data. It's all on a kind of a high-level thing. I also show a little code, but not too much, just a few snippets. So first, the Streams API provides the concept of streams. Streams are aggregator, of course, we're doing stream processing. And if you're familiar with Kafka, Kafka has the abstraction of a topic. And you can read a topic in Kafka Streams as a stream. That's kind of a high-level abstraction. So you build on top of that. And that is a stream as you know it from all other stream processing frameworks you have. On the other hand, there are tables, because tables are everywhere too. And that's super important. Because you also want to do stateful processing. And tables allows you to build up state in your application. And we will see how you can, exploit this kind of streams and tables as first-class citizen in the API. So the data model of a stream is quite simple. It's a key value model, so we have data records. That is very similar to the underlying concept in Kafka, where you have also records or messages that also have key value models. So that's just like a one-to-one mapping process. So how do you deal with streams in Kafka Streams? Well, first, you can read a topic as a stream. That is what we're seeing at the top. And that's kind of a code snippet we have. So we have this object that we call a K-stream builder. That is your API that helps you to express your computation in a higher level abstraction. It's our DSL. On this builder, we call it .stream, and we give it a topic name. And then it will read the topic, as a stream, and the abstraction here we are using is a k-stream. The stream is fully typed. In this example, I have long as the key type and string as the value type. And now you can say you want to apply some computation or transformation in the stream. So in this example, I do a very simple transformation where I say I want to map the values. And for each record I get, I take the value and I convert it to a lowercase representation. And then I get a result stream, that's the output stream. In this case, it has the same types, but of course you can also modify the types. And you can apply much more computation than that. And then finally, in this example, we say, well, we write it back to a Kafka topic. So we say output stream.2, we specify topic name, and we write it back. And that's very simple transformations on a stream. You start with a stream, you transform it, you get a stream, and you can write it back. Now I also mentioned tables. For tables, it's similar. We have the same builder pattern, and now say we want to read a topic, but now we don't read it as a stream, we read it as a table. And what this means is we apply different semantics to the data that is in this topic. And we say, actually, this topic we are reading is a changelog. It's not a stream of facts, as in the example before, where you have a record stream. Every record represents a fact. Now with actually the changelog, it represents updates or deletes or inserts. And what we can do when we read it, we can materialize this in a key value store and build up a table representation, a physical table representation. And when you apply a program like this, you get very, very powerful semantics. Assume, as an example here, you have a topic that contains data of your customers. And you say, in your stream computation, you need this data. So you have a topic where you have an ID of your customers, that's the key, and then you have a JSON, that it's more information, like address and email address and telephone number and stuff like that. Now you can read this as a table, and you get a full representation of all your customers. Now when you update any of those information, what you would do is, you write a new record to the topic from some external update service. And Kafka Streams automatically will read this record and will update your materialize to you in your application. And that's of course very powerful because it's basically caching your updates and materializing them, but you don't have to worry about cache invalidation and all those kind of things. So you get a local representation, and it's updating automatically without any need for you to investigate. You just write the change to the changelog topic, you read it, and you get it into your application. If you have this, then you can do more powerful operations. In this example, we are joining a stream and a table together in order to enrich the stream. Again, we have the example of our customer that we did read as a table. And, or in this example, it's a little bit different. We have a dimension table. I mean, it's similar, and you have facts with kind of IDs, and you want to enrich those facts with these dimensions. Then you can join it together. That would mean here we have the enriched stream. That is the result. We take the input stream. We join it to the input table. That is what we just read in, and we get an enriched stream. And for each record that is coming in, it would do a lookup in the dimension table, figure out the correct record, and do a join. And that's also quite powerful because if you remember, the table basically updates in the background. So if you take the example from before, if you say at a certain point a customer makes an order and you place an order into your fact stream, then you join it with the table and you join it with the current address. Later on, the customer updates the address and places a later order. The second order will automatically join with the updated address. And the result here is again an enriched stream, and then you can do further processing as well. I also mentioned aggregations, and that is my next example I have. So if you say you have a stream and you want to do an aggregation on top of the stream, then you would say, well, I have my enriched stream. First, I group my stream by key, and then I want to do some counts. In this case, your record stream comes in, and the result will be a k-table again. So first, we use a key value store internally to materialize the current key of each count, of each record, and we update this with every record that comes into the enriched stream. And at the same time, every update we are applying to the materialized view, we are sending downstream for further processing. So your downstream application can react and always gets updated what is the current count for each key. And this also shows that this kind of k-table concept is kind of a dual thing. On the one hand, it's a materialized store, and on the other hand, it's a changelog stream of updates. Okay, if you build an application like that, this would all compile down into a processing DAG. It could look something like that. You have your input streams, basically two topics you're reading, you apply some operations, you get some stateful operators in between, and then finally you write it to the output topic. So this is a classical read process write pattern we have, including updates of the state. And in Kafka, what does it actually mean is, well, for reading, you need to track your input offsets. You need to know how much data have you already processed and got from the Kafka cluster. Then for processing, the hardest part is the state update you need to track. And then finally, you need to also be sure you have written your results to the output topic. And in order to get exactly once, all this must happen all at once or nothing. So if you only do part of this, you have errors in your computation. And I will go through a few error scenarios in the next slides. So first error scenario is tracking offsets. So let's say you're reading data from your Kafka application. You read the first record, you process it, you have some output, and finally you commit your offsets to say, okay, I have processed record 1. So far, so good. Now you're reading the second record, you do the same thing. You process, you write your output, but before you can commit the offset, you're crashing. So now the application basically recovers and says, oh, where did I left off? And it says, well, the last record I read was the first record, because the second record was never committed. That means now you reread the same record, you process it again, and you write it a second time to your output topic. So this duplicate reads basically lead to duplicate writes. So that's the first thing that can go wrong. Similar scenario, now we have a stateful computation. Again, we read the first record, we process, we update the state, we output to the output topic, and then we commit. So far, so good. Now, we read the second record, we process and update the state, but before we write to the output topic, we actually crash. Okay, we don't have a duplicate in our result. That's great. But, well, we modified our state. So when we now do the same thing again, we actually start with a corrupted state. And when we reprocess this record and write it to the output topic, we get a wrong result. For simplest example is an overcount. And you can do. Okay, last scenario. That's a little bit more subtle because that's not very related to your application. You have a producer application that writes to your topic, and you have a consumer application that reads from this topic. So when you call send on your producer, what could actually happen is that there is a glitch in the network. And the record actually is written to the topic, but the producer never receives an acknowledgement. So what the producer needs to do is, it retries to send the record again. And this can also lead to duplicate writes in your topic. And of course, if the consumer application downstream then consumes it, it consumes a record also twice, and those duplicate writes lead to wrong results for downstream applications. And the point I want to make here is, usually you have deep pipelines, so it can go all over the place. And before Kafka had exactly one semantics, it was your responsibility as application developer to take care of all this and to avoid it. But with exactly once, and with the Kafka Streams APIs, it makes it very easy to use, you get those exactly once guarantees, and you get an atomic read process write pattern that Kafka Streams library provides. And this allows you to build these deep processing pipelines, and you can be sure your data is processed with no errors. An important thing is, of course, if you do this, you have kind of say within the Kafka universe. If you have any side effects, let's say your application is seeing a record and you're sending an email and you crash in between, that's a side effect. You reprocess, you send the email a second time. That's something we cannot prevent. Only if you read and write your result back to Kafka, you can of course guarantee that the write to the output topic is only done once and not twice. It's kind of important to know. Okay, so a few more details. So exactly once builds on top of the Kafka producer and Kafka consumers. And in 0.11, that was the version when exactly once was added, Kafka adds a new producer API, the transactional API, and it also enables the producer for idempotent writes. What this basically means is when you enable idempotent writes in your Kafka producer, this duplicate writes I mentioned before, because an acknowledgement get lost, cannot happen anymore. The Kafka producer will attach a unique UUID to all of your records, and in case something goes wrong and it sends a record twice, the broker can detect the duplicate write and will drop the message on the floor. This is a very nice property, and it's basically the building block for the transactional API, because in the transactional API, that is required to do this read process write pattern. If you use the transactional API, you can say on a producer, I want to start a transaction. Then you can write multiple records to different topics or partitions, doesn't matter, into the topic. And then finally you would commit the transaction, and this commit would be an atomic write to all of those. And the important thing here is you might know that if you commit offsets via the Kafka consumer, it commits offsets into a special topic in the Kafka cluster. And that means we can actually piggyback committing of the offsets within the same transaction, because it's just a write into another partition. So if you use the lower level producer API and you have read process write pattern, you would not use the Kafka consumer to commit your offsets, but you use the producer to do that, and there's a special API for that. Another important thing is, of course, if you say you have a running transaction, you can also abort it. So the consumer now also has a new mode that is called the read committed mode, where it will ensure that only committed data is returned to your application. So if you crash in the middle of an application and parts of your data was already written to the topic, the consumer will never see it, or will never return it to your application. And that's also configurable. You can also say go with read uncommitted mode, so you read everything. So how do you use this in practice? A few more details. For the Streams API I mentioned already, it's just a configuration parameter you set. We don't need to change any code. And all the nitty-gritty details about transactions and all the things is done internally for you. If you go with lower level APIs and you use the idempotent producer, it's also just a configuration. Also no code change required. Only if you want to go with the transactional producer, there is a config parameter, that's a transactional ID, that identifies your producer, and all your transactions this producer does will use this ID. So it must be unique in the whole Kafka cluster, otherwise you have a conflict. And then there's the transaction API. I will show how it looks like on the next slide, just briefly. And it seems very easy on the surface, but it's actually pretty hard to use correctly. So that's also the reason why we actually recommend to use Streams API, so you don't have to build all these things by yourself, but of course you can do that. Because, using the API as long as everything is right, it's pretty easy, but failure recovery is the hard part. And then finally, for the transaction consumer, it's also just like a configuration parameter you can use. It's called isolation level. By default, it's set to read uncommitted, but you can set it to read committed, and then you can enjoy exactly one semantics there as well. So how does this transaction API look like? I mentioned it already briefly. So you have your Kafka producers that you initialize, and the first thing you need to do is you want to initialize a transaction. So it registers the producer to the broker, and then the broker is able to start transactions on the producer, on the broker. Then if you want to start actually a transaction, you call begin transaction, and then you can send records, and all those records are part of this single transaction. And as long as you don't commit or abort the transaction, this data will never be shipped to any consumer. Then we have the special API I mentioned already, send offsets to transaction. That is this commit API that you can use, where you can piggyback offsets of your input topics to your transaction. And then when you're happy and you want to commit, you just call commit transaction. And this will issue a two-phase commit on the broker side. And then the data is available. You can also abort a transaction. With abort transactions, I mentioned that already. In this case, all the transactions aborted, and the data that is already written will never be delivered to a consumer in read committed mode. Another thing is, I mentioned already that the transactional ID must be unique in the whole cluster. So if that's not the case, then one producer could actually kick out another producer when one producer calls any transaction. So only one producer can use this ID. And in this case, the other producer would get this new introduced producer fenced exception that you also need to handle. So in this case, some other producer is using the same ID, and you have failed to die basically. So to summarize this, Streams API is the easiest way to build applications with Apache Kafka in general. The main takeaway message here is that it's a library that is enriching your application, so you don't need a computation cluster. So it's a completely different model than all the other stream processing systems out there. We provide end-to-end exactly once guarantees on top of the Kafka cluster, and this strong semantics simplifies the application development because you don't have to write all this deduplication code that really is kind of boilerplate actually, because you want to express your application logic and not take care of those details. I also have one more slide about material. So if you want to try this out, I would of course recommend to go to Confluent open source to get a richer ecosystem instead of vanilla Apache Kafka. You can also check out our docs. And if you're interested in more details about exactly once, we have our blog. I have a link here that is very interesting. There were also 2 talks about exactly once on the Kafka Summit in New York this year and San Francisco. And what might also be very interesting, because it also exploits exactly once the building application, it's a blog post about microservices on top of Kafka using the Streams API. And there was also a talk at the Kafka Summit, where you can also find the link here. With this, I want to close and thank you. And if you want to learn more about this, I have like 50 backup slides with more details, so feel free to ask anything. Thank you.
Any questions for Matthias?
So, there's Kafka Connect also that exists now. Do we get these exactly one semantics with Kafka Connect as well?
Not yet. It's in development basically. But so the problem with the connectors is a little bit different because you get data from the outside. So right now, with this read process write pattern, you're kind of in a closed system. But if you connect to the outside, of course, well, you don't want to have a cross-system transaction. So it really depends on the system. So there's work in progress to exploit it. For example, idempotency can be exploited very easily. and also transactions to some extent. But of course, the whole pattern is a little different. So right now, it's not there, but it's coming.
So maybe to state the obvious, so these analytics on top of, they wouldn't run on top of Kinesis, right?
Yes.
Or they do or don't?
No, they don't.
They don't.
So Kafka Streams is part of the Apache Kafka project. It's not a separate project.
Yeah.
So, and it's deeply integrated with Apache Kafka, so with the brokers.
Yeah. And that's interesting in itself, the notion that, something so beautiful as Kafka Streams itself, all of a sudden it's kind of like being bundled into this other thing. It seems like there should be more decoupling. Is that not possible, or what am I missing?
No, why should it be possible? I mean,
well, for example, I use the registry by itself, and it's great. But I don't have to use a stream for that.
Well, you don't need to, yes, that's true.
Yeah. Okay, so I guess as a trend, these projects seem like everybody's trying to do everything. So like even like Spark wants to do BI now.
Yeah. I mean, the point is really if you look at those systems, and especially Kafka. So from my point of view, if you have the brokers, you kind of have a storage layer, if you wish, and then you have compute on top of that. And with also this big data development, you have a Hadoop, and then you build this kind of different executions engine on top. Actually, it's like building a database, but not having a runtime on top of it. I build a database storage layer with tables, and now plug any kind of runtime on top of that. And that's kind of not optimal, because if you build a whole stack, you can deeply integrate it, you can have much stronger assumptions, and you can build a much better system. And that is actually what we are aiming for with Apache Kafka, to have an end-to-end solution, and where you don't have to plug in like 5 different systems to make something run, because you have a storage system, a completely different runtime, and then, for example, even a different higher-level SQL layer on top of that compiles down. I mean, that's also why we built KSQL. KSQL actually, in fact, compiles down to Kafka Streams application, so it's kind of one stack.
So we get the guarantees, and we have to buy into the full stack at some point.
Yeah, I mean, sure. I mean, if Spark says, well, we know transactions are there, and we use Kafka Consumer and Kafka Producer, and we leverage these APIs, they can do the same thing, of course. Sure. I mean, there's no login or whatever. I mean, it's an open source project. You can build on top whatever you want.
Right.
But I mean, this capability of Kafka Streams being a library is kind of something nobody else has. And I mean, that frees you from deploying 2 clusters. You just go with Kafka.
So, is there an incentive to keep or start using the consumer API now that the Streams API?
One second.
Like, assuming you have an application already using the consumer API, would it make sense to move to the Streams API, or is there any significant?
It really depends on your application. I mean, if you have a running application and it just runs fine, I would say no need to rewrite. But if you start something new, especially if it's stateful, it makes a lot of sense to use Kafka Streams, because Kafka Streams does handle stateful, and it's completely fault tolerant. So, and that's also the thing how Kafka Streams actually scales. I didn't have a slide for it because I cannot do a complete introduction, but if you want to scale your application, you just start the same application on multiple instances of it. And because internally it's using the Kafka consumer, we exploit the group management protocol to share the load of all those instances. And if one instance fails, we detect it, and if it hits state, we can move it over to another instance, recreate the state, all backed by Kafka. And you don't need to do anything for that. You don't need to write code. So I would highly recommend it. Otherwise, you have to deal with those things by yourself, of course.
I'm curious how you are fault tolerant on the aggregation tables. How do you manage that? Is it stored in a system?
I have a slide for that. No, basically we are leveraging a topic. So what you have seen here, and you can go back to that slide that explains very good. So what you have seen here, you're doing the aggregation, you're doing the mutation, and as a result you get this change upstream. And what we do is, in the background, we also write this changelog team automatically to a topic. And then it's preserved. So, and that also means that the store here is really just a cache. Your data lives in Kafka. And if the cache goes away, we reread the changelog topic to recreate the state.
So you have to read the whole topic again then?
Well, not necessarily the whole topic. So first of all, if you use a changelog topic here, we use log compaction. So if you have an aggressive compaction policy, the size of the log will be the size of your key space, of course, because we compact it. And the other thing is, what you can also do is, you can configure so-called standby tasks that maintain a hot standby on a different instance by reading the changelog topic while the computation is running to refresh the state, and if one goes down, you have like a very quick failover because the state is already there.
Any other questions?
Okay, then one more thing. We have still some slack left. So if you want to grab one, some t-shirts or stickers. And if you have more questions, I stick around here for a few more minutes, so feel free to talk to me.
Right, and we're going right to the raffle right now for the Amazon doc, so we're going to do that next. Thank you, Matthias. Thank you.